Eins, zwei. Yeah, good afternoon. I'm very happy to heralding this talk, or rather the series of talks. The following 3 talks in this hall here are about GSM. GSM is the mobile phone system that we all using since probably 15 years now. And as it is with all technology, in the beginning it seems very complicated and very difficult to master. You don't get the hardware, you don't know the protocols, it's all complicated and difficult. And after a while, after putting energy to it and meeting the right people and reading and building stuff, it becomes manageable. So this series of 3 talks about GSM serves one big purpose, which is to prepare you for the fact that GSM is broken in a way that it only wireless LAN without anything is broken in terms of other technologies. So GSM will end up in the hands of kids with laptops sniffing down your block to everybody else's phone call. So the 3 talks are split along a bit of a logic. So the first part is about OpenBSC, which is the software behind the network, the GSM network that is running here on the camp. The second part is about a piece of software that's called AirProbe, which is a GSM sniffer that works based on GNU radio components on the USRP, meaning that is software that you can decode the bits from the air. And the third talk is about how to decrypt the bits that you sniffed with AirProbe from the air and break the little bit of encryption that is still there on GSM. So the first 2 parts will be done by Harald. Oh, and we will have an approximately half-hour question and answers at the end of all talks, basically in 2.5 hours. There will be a long question and answer session of all participants.
Can somebody? Now, okay. So welcome everyone to the talk on OpenBSC and how to run your own GSM network. As most of you will have noticed by now, we are actually running our own GSM network at this very event. This presentation is about the technology behind it, the software that we use, and the actual setup of the network here, and the kind of implications and the meaning of it has for IT security, and particularly cell phone security, if people can now run their own networks. So first of all, why would you want to run your own GSM network? Well, basically for the same reason that you run other networks. I think when I was probably 12 or something, I was connecting 2 PCs over RG58 Ethernet, and I set up my first computer network just because I wanted to play with network technologies and explore Ethernet and TCP/IP and so on. And there are other networks which are not based on Ethernet, which nonetheless have the same widespread global nature, which is, for example, GSM with its protocol stack. And why should you be able to play with one network technology and learn about it, educate yourself about it, but not about the other one? So it's about learning and experimenting with technology. And also, obviously, at least for me, being somebody very much involved in the free software community, in the free software community, not many people have managed to do that before with free and open source software. Obviously, I'm sorry for the missing carriage return at the end of the slide. Obviously, once you run your own network, you actually have the foundation of being able to practically demonstrate already theoretically known GSM security problems, right? You might go online and search for GSM security, and you might find some papers, and maybe somebody has written that theoretically you could do this or that, but how do you actually do it? And for many of the attacks, or even for learning how the technology works that you use in these attacks, you actually have to have your own network to be able to play with it. And so for me, it's sort of building the foundation of enabling myself and other people to do more security research in GSM, which in the end will be the necessary means to achieve more public awareness about the lack of security in the GSM network. If you look at today's internet security, where if you do online banking or anything sensitive, you use SSL-based encryption with reasonably well-designed ciphers and so on. Yes, of course, we have just heard yesterday the various certificate problems and implementation problems and so on. But in general, the security level you have when communicating over, state-of-the-art internet technologies is so much higher than if you use GSM. And that's something that many people don't really realize. And unless we are able to run our own network, and on that network be able to demonstrate security problems in a way that the general public realizes there is a problem, we will not change anything in this current situation of insecurity. So, legal disclaimer, don't try this at home. GSM operates in a licensed spectrum. It's not like Wi-Fi where everyone can just put up his own transmitter and receiver. So since it is a licensed spectrum, in order to operate your own GSM network, you need approval from the respective regulatory authority, such as the, I don't know how to pronounce Dutch correctly, but here in the Netherlands it's the Agentschap Telecom. And so they need to give you a license to actually use that frequency. So if you want to do any of the things that I'm describing here, first get approval from the regulatory. If you do not, use your transmitting equipment with dummy loads. If you put a dummy load on your transmitter, you can still receive it with a phone in like a meter distance. That's okay, right? But it's not, going anywhere in the vicinity. And especially do not interfere with operators. The whole point of running your own network is to be able to do security research without interfering with the production network. So you can demonstrate and prototype something and then raise attention about it. It's not about actively disturbing commercial networks. The software we wrote is strictly for research purpose. It's not meant to be a professional, high-quality, robust, high service level, whatever, GSM network software. It's written as a research tool, and it's written with that kind of concept in mind. Even though you can see it can be used for a network of the size of this camp, where we literally have more than 400 GSM phones right now using the network, making calls and doing SMS. So a little bit of background about the GSM network architecture. Unfortunately, there is no hitchhiker's guide to GSM network protocols. The literature you can find is typically very high level. This literature addresses people who want to deploy GSM networks and who want to decide where to put their cell towers and in which distance, how to organize their network, these kind of things. So if you want to work for an operator and deploy and manage the network, then that's the kind of literature you need. For implementing the GSM protocols, there's very little useful literature out there. On the other hand, the entire protocol specifications are publicly available for download. You can just go to the ETSI or the 3GPP website and download those specifications. But at the time I did this, it was 1,108 PDF files and 414 megabytes of total text. I don't know the number of lines or whatever it is, but it is a lot, as you can see. I mean, only those specifications that we definitely need to use for a minimal network setup, the specifications easily go to somewhere, I would say, around 2,000 to 3,000 pages. It's the absolute minimum subset of the protocols. So how does this entire network work? A number of people in here will already know some of that information because you might have had some GSM communications lecture in your university course or something. I'm sorry for that, but still many people do not know the basic architecture of the network, so I have to make this slight excurse as a slight deviation into what the GSM network is and how it works. So first of all, like all traditional telecommunication networks, it is a bit synchronous network, which means everything is synchronized. It's the same like an ISDN or SDH network where your phone at home and every other phone that is connected to the same network operate on the same synchronized bit clock, and everything is centralized clocked. The layer 2 on GSM, and I'm talking about the layer 2 of the air interface here, is modeled after Q921, which is the LAPD protocol also used in ISDN networks, which many people are at least a little bit familiar with. And the call signaling is modeled after Q931, which is the layer 3 protocol on any ISDN line in Europe, at least. I think generally, sort of, everywhere. There are many more protocols for mobility management, radio resource management, organization and maintenance, and other aspects of the protocol. Also, it is like other traditional telecommunications protocols that the intelligence is in the network, not in the end nodes, right? The TCP/IP internet differentiates itself very much from other networks that existed before or that existed in other realms, such as GSM or traditional, ISDN or other networks, where in TCP/IP, the internet paradigm is the end-to-end. You have stupid machines in the network which just pass packets from left to right, and the intelligence of the protocol stack is in the actual end nodes. Whereas on GSM or other telephone protocols, the intelligence is in the network, and the end equipment, which is your handset or GSM modem or whatever you might use, is a very, very stupid device that only executes what the network tells it to do. It's a very like master-slave kind of architecture. And GSM is also what I would call a TDMA nightmare. If you have worked with Ethernet or related technologies such as wireless, 802.11 wireless networks, or even Bluetooth or whatever other protocols, you typically have a packet, and each packet contains the source and a destination address, source and destination MAC address in case of Ethernet and related technologies. On layer 2 and on layer 3, you have a source and destination IP address. In the GSM network, you don't have that. Each packet really only contains the payload of the packet, and depending on which time frame it is sent, which time slot, in which frame, in which multi-frame, in which hyperframe it is sent, determines to which receiver it goes. So basically, you pre-configure mappings, which particular time slot on the air interface gets delivered to what particular subscriber. If you do not know this kind of setup, if you don't follow this setup, you will not be able to make any meaning, like what is this data, who does it originate, whom does it go to. This is all out-of-band information. So this makes it very different from other things that you might have been working before. The GSM network architecture has a number of core elements, and I'm introducing this terminology also in this presentation to be very clear and to use the same terms that everyone else uses that deals with GSM networks. So the phone is actually called MS. It's the mobile station, and what you generally call the cell tower is the BTS, which is a base transceiver station. And that base transceiver station connects to, over a wired interface typically, it connects to a base station controller. And the base station controller itself connects to the mobile switching center. So you have a hierarchical structure where many phones access one BTS, and a group of BTSs accesses one BSC, and a group of BSCs access one mobile switching center. And then you have auxiliary elements such as the home and visitor location register. I'm going to talk a little bit about the individual elements here. The BTS, as the name indicates, it is a transceiver. Many people call it a base station, which I personally think is not entirely correct, because it doesn't really do much. It's really just a transceiver. So it receives a packet on the air, and it encapsulates the packet into a different protocol and sends it off on a wired interface. And if you get a packet from the wired interface, then it decapsulates that and sends it onto the RF layer. So apart from scheduling the time slots and configuring transmit power and these kind of things, it doesn't contain any protocol intelligence. It doesn't know anything about calls or phones or any of that sort. So basically, you can think of the BTS as nothing else than a remote Wi-Fi card that is not inside your PC, but it's this big box sitting over there, right? And instead of plugging into USB or plugging into a PCI bus, it's this Cat5 cable that runs to this box. So yeah, it is a transceiver. It handles the layer 1 and some parts of the RF layer 2. It handles the actual modulation and demodulation of the RF signal, the time multiplix, the scheduling of frames, but as I said, a true slave to the base station controller. The base station controller is the actual instance that manages the radio resources, that determines which channel to use for which subscriber, do the allocations and these kind of things, resource management. It does most of the actual decision-making when it comes to utilization of your RF layer. It controls the BTSs, and it also handles handover between BTSs that are connected to the same base station controller. So if you have, like we have here, we have two base transceiver stations. They are connected to one base station controller. And the base station controller would be in charge of noticing if a handset and a mobile station moves from one BTS to the other. The mobile switching center is taking care of the calls itself. So if you make a phone call or you receive a phone call or anything like that, the actual call control protocol is terminated at the mobile switching center. It is also taking care of what the protocol specification calls interworking. I've also read international interworking before, or inter-protocol interworking. So basically meaning that it is some kind of interface to ISDN or other telephony systems. And it does things like handing over calls between multiple BSCs. You have the HLR and VLR, which stores the data about the subscribers. As you know, in GSM, you have a SIM card, and the SIM card is basically, it represents the subscriber to the network. And the home location register stores the information about which SIM cards the operator has issued, and whether those subscribers are currently attached to the network or not, which MSC they're using, and so on. Also, the visitor location register handles visitors, such as people roaming in from other networks. Let's look at the individual interfaces, just the ones that are important regarding this running your own GSM network business using OpenBSC and like we're doing here. First, there is the UM interface. UM is the air interface between your mobile station, the handset, and the BTS, the only RF interface specified in GSM. The layer 2 is derived from the LAPD protocol of the wired ISDN world, and the layer 3 is specified in GSM technical specification 04.08, and it handles stuff like radio resource management, mobility management, and call control. The interface between this BTS and the base station controller is called ABIS. And it uses an E1 physical layer, which is this primary RAID interface ISDN, which has 30 usable time slots, 64 kilobytes each. People who have used the ISDN in larger scale before will know the E1 lines, 2 megabit total bit rate. On this physical layer, there's a layer 2 management TEI entity that is very similar to what you also use in traditional ISDN. So this TEI establishment procedures and that kind of stuff, which you see on a typical ISDN D channel. In addition to that, you have 2 more protocols. One of them is the OML, the organization and maintenance layer, which you use to set up the actual BTS. You configure things like what is your maximum transmit power, what kind of frequency should the BTS be using, what is your channel configuration, all kinds of information like that. You set over the OML layer. Also, this is for event reporting in case of a failure, like your BTS says, oh, somebody disconnected the antenna, I cannot send anymore. You get an event report. Also, stuff like changing the BTS firmware. This is all organization and maintenance layer. The actual interesting part during operation of the network is the radio subsystem layer, the RSL. And RSL is used to actually open and close channels, to configure the encryption that is located inside the BTS for the air interface and so on. This is for the signaling part. The actual voice data is transmitted in what is called TRAW frames, or TRAW frames in English probably, it puts those TRAW frames into other E1 time slots than the one it uses for signaling purpose. So this is a slide about the time multiplex on the ISDN primary rate interface. You have 32 channels. One of them is used for synchronization and error handling, and the other channels you have available for actual payload data. Every BTS uses one of these channels for the signaling, OML and RSL, one of these time slots. And then you use, for every 4 on-air time slots, you use one additional E1 time slot on the wired interface. I'm skipping that. You can look at the details of the presentations later. So this RSL, it contains messages for the radio link layer, which is basically the layer 2 on the air interface, where you get stuff like, oh, a packet has arrived and I have to acknowledge it, or a packet has to arrive which does not need to be acknowledged. This kind of stuff you get there. Then you have dedicated channel management messages. A dedicated channel is a point-to-point channel between one mobile station and the network. If you're currently making a call, or if you're currently receiving or sending an SMS message, then you will be assigned a dedicated channel from the network, and this is what the dedicated channel messages are for. There's also common channel management messages, which are for not point-to-point channels, but actually point-to-multipoint channels, such as a broadcast channel. Every GSM BTS has a broadcast channel over which it transmits what some people would call beacons. In GSM, they're called system information messages. So constantly, it broadcasts information. Well, I am a cell. I operate on this frequency. I use this network code. My channel configuration is like this. All kinds of information that the telephones need in order to actually access the network. And that is using the common channel messages. And then there's transceiver management messages on AVIS RSL as well. The radio link layer itself, then, just to go back on this. So we have the E1 physical layer, we have the layer 2 TEI management, and we also have the RSL as a layer 2 on that E1 line. And inside the RSL layer 2, you then have the radio link layer header, and from the radio link layer header, you end up in call control, mobility management, radio resource, or SMS messages. So those are the interesting protocol levels, which is actually exchanging signaling information between your mobile station and the network. They're mostly specified in 0408 if you want to have a look at the details of these messages. The equipment we use for BTSs is a Siemens BS11 micro BTS. I'll have pictures just in a second. The Siemens BS11 micro BTS is built in '97, so it's already 12 years old equipment. And at that time, the term micro BTS was used for equipment that has a weight of 47 kilograms. That's the micro BTS. Right? So you can imagine how big at that time the actual BTSs were. Because if you think about the complexity of this protocol and that it has been designed in the 1980s and deployed in the early 1990s, the technology you had available at that time, you needed massive electronics to build such a system. The Siemens BS11 is a plain 2G BTS, so it has GSM voice calls and it has circuit switch data and obviously SMS, but there is no GPRS, no packet data communications, and there is especially no edge or 3G or anything like that. It has 1 or 2 transceivers, which you can each configure from 30 milliwatts to 2 watts transmit power in the GSM 900 band. There's 2 E1 interfaces. Why 2? Well, one goes to the BSC, the base station controller. The other interface, you can go to another BTS, because a BTS with 2 transceivers only uses about a quarter of the capacity that an E1 line has. So you can run your E1 line first from the base station controller to the first BTS, then to the second BTS, then to the third BTS, and so on. So you don't need a star architecture. The documentation is under NDA, but who needs that documentation if 99.9% of those protocols is in the GSM specifications? It literally is that far. There's only very few messages that are vendor-specific, and initially we just carbon copied them from existing traces. We didn't even know what they do. By now we understand what they do, but so you don't even need to understand those vendor-specific bits. It's very, very little. It's an RS-232 serial port for a local maintenance terminal, which is basically a local terminal which you can use to configure, do some initial configuration. There is a proprietary software for that under NDA, but you don't need that for operating the BTS. And we have a free software implementation called BS11 config, which basically does what the LMT would do, but it's not proprietary. If you open one of these, I have a picture of a closed one as well. If you open one of these BTSs, there you will see multiple units in there. It's an RF power amplifier, LNA, baseband, power supply, transceivers, and so on. You don't actually have to open them, obviously, but then, well, we did open them, so I thought I'd show you some interesting pictures. This is the stacking from the side. As you can see, each and every PCB is covered in a massive block of metal for shielding and even more so for heat distribution. This unit consumes more than 200 watts of power and is only passively cooled by metal elements. There's no fan, nothing inside. The typical operating temperature of the device is so hot that you cannot touch it on the outside. You will burn your fingers, but this is normal operational temperature. No plastics here. This is again from the side. You can see more shielded boxes and SMA connectors. You can see coaxial wires and serial lines. This is the connector panel where you actually connect the transceiver. The antenna here is RX1, RX0 is the 2 receive antennas. TX1, TX0 is the transmit antennas. And here, those fancy twin-ax connectors is for the E1 line, the 4 you have here. And then there you have a couple of jumpers and auxiliary connectors. And this guy at the bottom is the power connection. Yeah, 4-pin power. Amazing. It's just regular AC power. No, nothing fancy. It's just a connector that is fancy. So how did we go about this? Well, I bought one of these BS11s on eBay in 2006. I started to read some specifications. I built the cables that I needed. And I bought an E1 card that I can plug into my Linux PC to actually establish a physical layer connection. I also found an ABIS protocol analyzer for 99 euros on eBay. Apparently nobody really needs these anymore because the modern GSM networks have different interfaces. So I contacted with some other people who also bought these units off eBay. And I found somebody who was able to provide actual protocol traces of the ABIS protocol. So I had the spec and traces that were supposed to be captured from a real-world BS11 that was working. And doing that, using those two things, it would be possible to do something. Unfortunately, around that time, I had a lot of work for OpenMoko, so I didn't really get any further at that point. Until last year in September, a person called Dieter bought another BS11. He also bought the E1 card, and he started development also using the same traces that I had, and he made very quick progress. Apparently, he wasn't that busy at the time. So what he wrote is a program called BS11 init, which uses the reference code for DAWs that the manufacturer of the E1 card provides. And so this software directly accesses the hardware. It doesn't use any driver layer. It doesn't use interrupt. It constantly pulls the hardware. He ported that to Windows, and I ported it successively to Linux, just memory mapping the registers of the hardware into user space. And it was a proof of concept code based on challenge response. Basically, he looked at the trace, okay, this is happening. So, well, if I get this from the BTS, this say, sequence of hex values, I send back this sequence of hex values. And just by doing this, challenge response thing, he was able to get it up, do the TEI assignment, and bring up the OML and RSA layers, which is quite an achievement just from replaying these messages. Later on, he added a little bit of code for performing the location update. This is registering a phone to the network and paging a single phone. But that's about it. And it was very, very flaky and early alpha level quality. But it was sort of, yes, we can work with this BTS. This is how it looked like. It was a text, ported from DOS, a text program that was running on Windows. And you had, 8 different actions that you could perform. And that's about it. In November and December last year, I started this project called OpenBSC, which is what I wanted to start in 2006, but then I was too busy, where basically using the proof of concept reference code and the packet traces and all the knowledge from the specifications, we got to actually implementing this halfway properly. So we use the proper hardware drivers. We use the MISDN ISDN stack that's inside the regular Linux kernel. We had to do a couple of patches, but those are now in the mainline kernel as well. We had to learn the sockets-based API and come up with an architecture for the entire beast. Being the person I am, there's no threads, single select loop, event-driven architecture. At 25C3, we were able to already have a minimal HLR. We could page mobile phones. We could configure our own network ID. So we could say, we are, Egypt or something like that. We did a lot of debugging and stabilization with more than 1,000 people, at least, trying to register the network. And we collected the IMSIs and EMIs of those phones, obviously. Because, this is one of the security or privacy concerns that we also want to make people aware of, that as soon as you have your phone on, anyone who claims he's a network without any authentication credentials can ask your phone, please tell me your IMEI, this is the equipment serial number, and please tell us your subscriber number, which is on your SIM card. So there's simply no provision or no threat model for a rogue network attack in GSM. The network is always trusted. Only the phones can be evil. That's the mindset of the people designing the protocol. So now in this year, OpenBSC really takes off. We add more and more features. We have SMS store and forward switching. We have stable voice call support for full rate and enhanced full rate codecs. We support more than one transceiver per BTS. We support multiple BTSs. We have a Cisco-like console interface, so you can say configure terminal and that kind of stuff. And you can show the current channel configuration or send SMS messages. We added support for more BTS models, not just the BS11. And also, we interface to a traditional E1 now, so we can actually switch calls from an ISDN network into the GSM network and vice versa. Obviously, also tons of bugs and stability issues. initially, we relied a lot on the phone behaving properly, which obviously is not a good idea because the phones are evil and they have lots of implementation bugs. So you rather have to make sure that if the phone thinks, well, oh, the network has opened a channel to me, I will never close it again unless the network tells me to close it, then you should have a timeout and this kind of stuff. We had plenty of resource leaks, both of RAM as well as on-air channels that were allocated and so on. And we finally uncovered the last bits of the Siemens ABIS proprietary Siemens ABIS extensions in like 2 or 3 weeks ago. The status today is you can have a GSM network in a box. You can run it on any PC, no particularly high CPU or RAM requirements, as I will show on a later slide. It doesn't need an MSC, HLR, VLR, authentication center, or SMS switching center. It's all in one software. You don't need all these components. The capabilities so far, well, right now here we are in operation of a network with more than 400 users registered to the network. We have multiple BTSs. Each of them have multiple transceivers. Voice calls and SMS implementations are fairly complete. We don't have in-call handover. So if you establish a call, like let's say at the lockpicking tent, and you walk all the way up to, well, let's say the CCC, a dome, then somewhere in the middle, the call will disconnect because we don't hand over an ongoing call into the other cell. There's no GPRS yet and no edge yet because that's one of the highest to-do items in our priority. So in the future, we will separate some of these parts. We will support an actual A interface to use legacy BSC or MSC or traditional MSC implementations. And support for GPRS and edge, routing of calls between E1 and IP RTP-based BTSs, and also interfaces for stuff like injecting packets from SCAPI. For one particular BTS, I already wrote that. It's called IP Access Proxy, I think, or Nano BTS Proxy. I don't even remember what I called it. But there's a proxy now which you can basically put between the BTS and the rest of the network. And with that proxy, you can inject packets both to the network and to the BTS. And to the BTS means also to the mobile phone. So using that proxy, you can send, for example, fuzz packets from SCAPI into the interface and fuzz either the network or the mobile station, which, as far as I know, on GSM, nobody has ever done, at least not publicly. Well, that's certainly a lot of fun to be had. Like right now, for example, all the phones that are logged in our network, obviously, since we are the network, we can also send them some random crap and see how they behave. We're not doing this, at least not intentionally. Our implementation might be broken, and we might send a packet that your phone doesn't like. I'm sorry for that. Well, if you experience any problem, you can come to us, and we will see if we can debug that using packet traces and see what's actually going on. But we could, and that's sort of the whole point of this demonstration is, somebody buying a 300 euro unit from eBay and using his brains and publicly available specification can run his own GSM network. And since there is no provision against rogue networks in GSM, he can pretend to be your network operator or anyone else's network operator, and can do all kinds of tinkering with your mobile phones and with the data that you send through those mobile phones. So how does this HAR 2009 GSM network look like? Well, first of all, as I initially indicated, GSM is a licensed spectrum. You cannot just, well, you can, but you will get a lot of trouble if you just put up an antenna and start transmitting, because you will be interfering with some commercial operator, and not only that, you will also violate law. And since the other operators had to pay billions of euros in order to operate GSM equipment, they will be very interested in shutting down everyone who has not paid these billions of euros. However, you can apply for test licenses. You can say, well, we have this software, we have developed this GSM software called OpenBSC, and obviously we need to test it in order to improve the software quality. and therefore we want a temporary test license, and that is what the organizers of the HAR event did. They applied at the regulatory authority of the Netherlands for a test license, and the license we got permits us to use 4 ARFCNs. ARFCN is a physical frequency on GSM, and we are limited to a transmit power of 100 milliwatts on each of these ARFCNs. If you remember a couple of slides earlier, I said that our equipment can do up to 2 watts, so we're running at 20%, we're running at 1/20th of that power right now. The mobile phones themselves, they all can also transmit at least 2 watts. So we are really running this at very low scale, and this also explains why sometimes the coverage is poor and your voice quality is poor, because you get a high error rate because the transmit power is relatively low. So, but this is all we could get for this event. The antenna height is restricted to 3 meters. Luckily, the license did not specify above which reference level, so we. Well, in the Netherlands, you could actually believe they meant above sea level, but we don't know. So what we did is, there's this nice hill. Okay, let's go up the hill and put it there. And we put it at less than 3 meters on top of the hill, and it was okay. In case operators get any interference, we have to shut down. That's basically also a condition. So far, we did not get any complaints. The regulatory authority was here, inspected the site, looked at our installation, and they were quite happy when they left. So apparently everything is fine. So the setup is we have 2 of these BS11 units. Each one has 2 transceivers. This is the technical details in case you're doing some on-air listening, what's happening. The BTS0 runs on 121, 123, and it has location area code 1. The other one is the other side. So the BTS0 faces, the campground where the lake is located, and the BTS1 faces basically this side of the hill up to the lock pickers and the OpenBSC tent. The antennas are mounted back-to-back on a tree. I have pictures right now, and the 2 BTSs share a single E1 link. So this is the 2 BTSs located at the bottom of a tree. Just tied them to the tree at the bottom. You have lots of cables going in and out. The black ones are radio cables. The gray one is the E1. The antennas are, put against the tree using duct tape. Please notice the special, PET bottle back here, which is glued between the tree and the antenna, because the tree is not straight, it is slightly angular, and we don't want to, cover some airplanes up there, but we want to actually go down on the area. So that, again, is from a different angle, the 2 antennas, facing to 2 different sides. And then we have a Linux PC running the OpenBSC software. It uses the MISDN driver. We have about 60 meters of Cat5 cable for the E1 line between the BTSs and our tent where the PC is located. The network ID we use is 204-42, which is Netherlands and the operator called 42. 42 was unused, and the regulatory authority said, well, you can use it. The typical CPU use we have is less than 5%, and the resident set size in RAM is somewhere around 3 megabytes, just to give you an impression how little resources computationally you need to operate a GSM network these days. It's just, back in the 80s, you needed these massive racks full of discrete TTL components, and today the machine here is some I think, 3-year-old Opteron with 1.6 gigahertz or something, nothing too fancy. So, and then you end up, in the tent, and inside this tent, our GSM tent, we have that actual machine, which looks like, I thought I had a picture of the machine, but I don't. I'm sorry. Some are missing from the slide. Well, it's a PC, right? It's a black PC. It has a couple of cables coming out of it. So, nothing too fancy. The registration procedure, I think a number of people have already been going through it. If you have registered to our network, you will know when you first log onto the network, you get an SMS message. And in that message, we will state a URL, your IMSI, and an authentication token. You go to the website, you enter your data, and this enables you for the network. If you do not go to the website and enter your data, you will never, ever get any other SMS from us or register again, be able to register again to our network. Because that's sort of the precondition we made to make sure that nobody accidentally ends up on our network. Right? There are people that do not belong to this camp in the vicinity, like camping guests and whatever other people, and all they get is the single SMS, and if they don't do anything else, then nothing will happen. However, if you receive the SMS and register, then we will permit you to use our network, and you can make and receive phone calls, establish SMS, and so on. Now, what can you do? Well, yeah, SMS phone calls. What can you do to play? Well, you can use AirProbe, which is the next talk just coming up, or other tools to actually decode and listen to the GSM communication, because now it is legal, right? First of all, we do not use any of the encryption or authentication that GSM networks typically use, so everything is plain text in our case. And secondly, we do not use frequency hopping, which also makes it technically more challenging to do eavesdropping on GSM communication. So basically, in this network, we lower the entrance barrier to hack it artificially, right, to basically show what you can do. If in 1 or 2 years the encryption has been completely broken, not only theoretically or algorithmically, but also practically, and then people can do that even on other networks which actually do have the encryption and authentication mechanisms installed. So since we do not have that, you can do all of that now as you want. And also, we don't do SMS filtering. So you can send any RPDU to any other phone. So using a data cable or a GSM modem, you can send all kinds of, say, well, the length is longer than the packet, and play tricks like that. We just transparently forward what you send the network to the recipient, and that's about it. What you can do is to help us to obtain, to test OpenBSC under higher load. The load so far is very, very, very low. Nobody wants to make calls. Nobody's sending SMSs. I would have expected much more use of the actual network. Well, obviously, by doing so, you also help us to obtain real-world protocol traces, which we can also use to, discover certain strange behaviors with certain phones, which probably might have security implications or not, but anyway, are interesting. The statistics so far, well, you see some fix-me's here. We weren't able to finish the statistics. So far, statistics module is not finished. But more than 1,100 phones tried to register to the network so far. More than 450 phones have actively completed the registration procedure. More than 1,000 SMS messages were sent. 450 phones, only 1,000 SMS messages. It's 2 messages per phone. Come on, what's this? You can do better than that. Use more bandwidth. Sorry? There are no services. Well, the service is that you can send messages to other people here. Well, I can understand that you need this, and I also need to implement this. But unfortunately, the regulatory authorities do not permit any test licensee to connect to any public network. Yeah. IP over SMS. Well, very happy to have you implement it. We're looking forward to your contribution. IP over short message carrier. Well, it's an exciting approach, especially since SMS can in turn be delivered over GPRS, so you get a very interesting protocol stacking here. I wonder whether the lawful interception authorities already have specified interfaces for that. Yeah, so anyway, we don't really know how many attempted voice calls we had so far. I don't know, what's the status of statistics by now? Apparently undecided. I'm going to continue. We can show, I have some graphs that I can show you. I'll just have to finish the presentation first. So if you want to learn more about OpenBSC or GSM in general, I recommend the following couple of links. OpenBSC is obviously the software we use. We have a wiki, we have a mailing list, we have a Git server and so on, the typical development. Apparently we have redundant microphones. The specs obviously, but they're, as I said, they're very dense literature. There is a guy called Joachim Göller from Berlin. He has, a homepage where he wrote some very interesting documents about GSM protocols, and I think for an introductory reading into the protocols, not GSM networks on an abstract level, like, this TDMA stuff, but actual protocol traces and explanations of protocol traces, you can go to that site and you can learn more about the actual protocol interaction. There is the THC GSM wiki, and obviously there's also OpenBTS, which is a similar project which also tries to, or is building a GSM network in a box, a kind of approach, just using different hardware than we are doing. OpenBSC is definitely also worth checking out. Now, a couple of thanks to Zeke, Alpha One, Stefan, and Jan for their work on OpenBSC. There's somebody whom I will just call W for his extensive ABIS protocol traces. Dieter Spar for his excellent input, Carsten Keil for MISDN, Andreas Eversberg for the LCR interface, and the organizers of HAR, whose name I still cannot pronounce, Stichting Hux or whatever, for getting the license. And obviously all the voluntary testers, I think many of them sitting in the audience. Now I have two pictures of, regarding stability, regarding statistics. Sorry. Where did I put it? I thought I had two pictures. I'm sorry. Where did I put it? Just give me 1 second. I'm sorry. We will put the statistics pictures online on the wiki and link them and so on. Basically, we have a couple of graphs showing the relationships of people sending SMSs, so social networking diagram kind of thing. Who relates to whom, who has sent what to whom. Somebody is sending messages, apparently. Very interesting. This is a test, SMS from an HTC Magic Android. Cheers. Well, thank you. You can see SMS is working. I will not show the graphs here. We also, as I said, it's a relationship graph where you can see who sent SMSs to whom, and you can also see a graph showing the number of attempted voice calls, the number of voice calls where we actually rang the other side, and the number of voice calls that were actually established over time at this event. We will continue to run those statistics and provide them also after the event is finished, all linked from the HAR wiki. Okay, then thanks for listening to this talk. Right now I'm going to switch my function or hat and talk about the AirPro project. But if you have any specific questions right now, very specific questions to the network that we're running here, feel free to ask questions now.
So we continue at 4 o'clock here with the talk about air probe, which is basically sniffing GSM of the air. Again, at 4 o'clock we continue here.